the first to introduce Nasir Mannan. He's going to come on. I know you guys have heard a lot from Nasir on these programs in the past. He's going to be instrumental in delivering this program. He's a principal engineer and directs CCAT's Advanced Design Automation Metrology Lab. So welcome, Nasir. We have Kristi. Kristi's going to come on now. She's a mechanical engineer and works alongside Nasir in a lot of these great technologies. I think you've heard from Kristi probably before. She does a lot of things out there as far as presentations and engaging with companies. And Sam Greenbank, and Sam's a manufacturing applications engineer, done some great work on the robots. I got a little sneak peek. I actually didn't know what I was looking at yesterday, but I saw the three of them. Kristi had the Hololens on, everybody's doing their thing, and I'm thinking, wow, it's going to be really cool today. So, and I know you guys are going to talk a little bit about the program and bring on some providers. So, you know, at this time, I want to let everybody know there's going to be handouts that are going to be provided to everyone. If there's any questions, you can put them in the chat room, and we'll follow up with those at the end of the presentation. So I think it's a good time to hand it over to you, Nasir.
Thank you, Ron. I appreciate that. Good afternoon, everyone. Thanks for joining us today. We've kind of broken up the first part of this presentation into three different subject matters. We're going to talk about collaborative robots first, so you have an understanding of the technology. And then we'll go into just briefly touching on 3D scanning. That's one of the sensors that we use as part of the automation workflow that we're going to be presenting later. And then we'll talk about the HoloLens. SphereGen will come on, and we'll just do a quick recap of that technology. That was another one that we use as an integrated solution to visualization, and you'll learn more about that. But before I get right into talking about collaborative robots, I just wanted to give a reminder that general use of any kind of robotics is always in an integrated environment, right? You always have a robot as one component to many components of a work cell. And so what we wanted to show here was how all these different technologies are working together, communicating together in order to reach the end goal. And in this case, it was, you'll see in the case study, for component repair and visualization of the data. How is the component repair coming along? To make decisions off-site, which has been very crucial, especially these days, and then how to actually visualize that data right on the physical part, so that you can kind of make decisions in real time. So that being said, Sam and I are going to kind of walk you through the distinction of collaborative robots from traditional robots. And one of the first things that you'll see is, particularly on this slide, you'll notice that both work cells here are showing traditional robots, but they have safety enclosures. That is one of the biggest distinctions you'll see, where there is, there's a limit. What this presents is a bit of a limitation on human and robot interaction, right? A person or a human has to be outside of the safety, has to be outside of that safety enclosure of the robot cell in order to run a program. And if anything is required by the robot, for example, parts to be placed in a bin or something where the human has to interact with the robot program has to stop, the robot has to come to a stop, the safety enclosure is opened, then some process is done by a person, they walk out, shut the safety enclosure and restart. And so you can kind of see here or imagine that either a person is working and then there may be some downtime of that person actually doing anything, and vice versa. So there's also the robot side where the robot's performing some work, and that for some momentary time it has to stop. If you go to the next slide, you'll see in this case with the collaborative robot, you don't have that safety enclosure. What this obviously allows is the fact that it doesn't need that level of safety. You have more human and robot interaction. Sam, if you want to say any additional words here.
Yeah, sure. So again, the primary distinction between a collaborative robot and a standard industrial robot is that from the beginning, the collaborative robot is designed to work alongside of people instead of an either-or situation. So they have the safety mechanisms built into the robot itself, and they do not rely on external safety mechanisms to keep the humans or personnel in the area safe. So that's the primary distinction, you know, as Nasir said, between a standard industrial robot and a collaborative robot. They're both very safe technologies. You know, it's how you go about implementing that safety. Go on to the next slide.
So here we wanted to show you a quick overview of the different types of collaboration that you can have with robots. You know, there are, for example, if you look at the graph there at the bottom left, this all the way to the left would indicate a low level of collaboration. And as you go to the right on the x-axis, that would indicate a higher level of collaboration. So the first one on the left there is the fence robot system, where a robot has a perimeter fencing separating workspaces between robot and worker, as we discussed before. And then you have the next one to the right is coexistence, where a robot has no fencing, but utilizes safety rated electrical sensors and scanners and has its own workspace. Then if you travel to the right in a little bit more of a collaborative environment, you have what's called sequential collaboration. Here, a robot utilizes safety rated electrical sensors and scanners and uses safety rated robot controls and also uses a shared workspace with the worker, but at separate times. And then you have the cooperation scenario, where force monitoring robot shares a workspace with a worker while both work on their own products. And then you have the ultimate, you know, the responsive collaboration, where a force monitoring robot shares a workspace with a worker, and both simultaneously work on the same product. Any comments here, Sam? All right, next slide, please. So that kind of brings us to you know, the design of the safety mechanisms for collaborative robots. There's various different ways in which a collaborative robot can be made safe for humans to interact with. You see, you know, on the top left image, you have safety rated monitoring stop. And here, a safety rated monitoring stop is basically an assured robot stop without removing power. And it occurs when a human worker enters the collaborative workspace. So the system here ensures that the robot and the human don't move at the same time, and is primarily employed when the robot is rapidly moving heavy parts through the workspace. The next one, we have a hand-guided operation. So here, before a hand-guided operation can start, a robot must perform a safety-rated monitored stop. During the operation, a worker is in direct contact with a robot arm and can utilize hand controls to move it. This operation is used for lift assists or highly variable tool applications as well. The next safety design is speed and separation monitoring. So here, you know, in this case, this collaborative work method is perhaps the most relevant. It allows the operator and robot to move simultaneously within the workspace by equipping the robot with sensors to monitor how close in proximity the worker is. At large separations, the robot continues to operate pretty much at medium speeds, but upon closer approaches of a worker, the robot reduces its speed, and at very close approaches, it comes to a complete safety rated monitored stop. And then we have the power and force limiting safety design. Here, power and force limiting are required in applications where there could potentially or intentionally or unintentionally be contact between a collaborative robot or any workpiece for that matter and a worker, when both are working in the collaborative workspace. Here, contact can either be quasi-static, such as the clamping of a part, the pinching of the robot arm or the work part and a worker's body, between the robot manipulator and a fixed object. Or it could be transient, such as the knocking into a part of a coworker's body where the worker is able to, recoil. So some of the key benefits and drawbacks of working with collaborative robots.
So when most people say collaborative robots today, they are referring to power and force monitored robots. And again, the entire design behind those robots are such that the robot should never generate sufficient force to cause injury to a person. So really, that methodology brings along several benefits when you're working with collaborative robots, and what makes a collaborative robot a choice that you would want to make for an industrial task. Probably the biggest benefit of collaborative robots is efficiency. And some of this comes from a couple of different things. For me, at least, the biggest one is the size of a robot cell. With a standard fixed robot, industrial robot, the guarding and fencing takes up a significant amount of floor space that is then not available to anybody else, to humans being able to interact in that space. That really limits the amount of usability that you can get off of a production floor. When you add in a collaborative robot, if the collaborative robot is not working, it doesn't need to have a fence that's in the way of people. In some cases, you can just move the robot out of the way and continue to work, and move the robot right back again when it's ready to move, when you're ready to use it. And that also really helps with interruption to robot workflow. As was mentioned earlier, a lot of times you need to perform a course correction on the robot, or you see something that the robot's not equipped to handle. You see a deformed part that the robot won't necessarily catch. You can very easily enter the cell or enter the work area of the robot and remove the faulty piece, or to perform some other corrective action without having to bring the robot to a complete program halt and restart the program. This also then allows, of course, immediate collaboration of handing parts to a robot, or having a robot unload parts, say from a machine, directly into a person's work area, where they can then immediately pick them up and keep working without any sort of a timed interchange. And that really helps increase the productivity of both the people and the robot, because essentially you're not waiting on each other anymore. You're not waiting for one person to vacate the workspace so that the robot can pick up and begin moving again. This especially has benefits when it comes to small and medium-sized manufacturers. And that kind of brings on some of the other positive aspects of collaborative robots, in that they're typically much easier to deploy. They don't require the extensive safety setup and training that traditional robots need. Their interfaces are designed to be much simpler and easier to use for novice users, so that they can very easily be redeployed and reprogrammed with a minimal amount of skill or expertise on the part of the operator. This in turn then helps increase ROI, because you no longer need to justify the price of a robot doing one task. A collaborative robot can very easily be reprogrammed to do multiple tasks without needing to go through an extensive setup and contact an integrator, get it set up and programmed. And it really helps with the overall flexibility of the robot and how it interacts with its tasks and with its workspace. And And to just in general, the flexibility. Most of these robots are relatively small. They don't require three-phase power. They don't require the safety, extensive safety setups that you needed before. So it makes them very easy to deploy and to redeploy. For instance, the cobot that we have here plugs into a standard wall outlet and is on a mobile cart that we can move around. You set it up to tend a machine for a shift and let it run, and then you come back in, say, the next day and say, oh, I don't need it to tend this machine anymore. I want to take it somewhere else. You just shut it down, unplug it, roll it over to the next machine, set it up, and have it run on another machine. It's very quick and easy to do that with a minimal amount of effort. But most of these benefits come with associated drawbacks. And the biggest drawback comes with the power and force limited robots. Because it needs to be safe, you need to limit the force. And the way that you limit the force is to limit speed or to limit payload, or both. So as a result, most cobots are slow when they're compared to standard industrial robots. A typical industrial robot will have a maximum speed of somewhere between 2 and 3 meters per second. A power and force limited robot, on the other hand, typically has a speed somewhere between 200 and 300 millimeters per second. And so you have a 10-time decrease in speed. That may or may not be a problem depending on what type of work the cobot is doing, but it is certainly something to be aware of. If cycle times is a priority, a cobot is probably not the best choice. The other drawback that comes along with this is payload. Most cobots have very small payloads when compared to their industrial counterparts. Again, it's a function of the force monitoring and how much force can be generated by a robot moving a payload at speed. A typical payload for a cobot tops out at 10 kilos. It's much more typical to see the 5 kilo range, which again is enough to handle a lot of parts, but the payload of the robot also has to include end of arm tooling, grippers, anything else that force that the robot may exert with the workpiece. If the workpiece only weighs 5 kilos, but you're pushing it into a fixture and you need to apply another 5 kilos of force, it's not going to work. And so it's something to certainly be aware of when you're working with collaborative robots, is that the payload is going to be quite a bit lower typically than industrial robots. Again, this may or may not be a problem depending on the particular application. And then finally, because the robots are designed to be simpler to use and simpler to program, they can sometimes lack the programming feature set that a standard industrial robot will have. And this is typically really only becomes a problem when you get into more complex tasks and complex logic and decision making. Things like being able to dynamically alter a path or trajectory based on sensor information, or being able to iterate, between multiple, select and run multiple program operations based on a fairly complex input. Usually the robots may be able to do it, but it becomes very cumbersome to program comparatively to an industrial robot. Again, this isn't typically an issue when you're working with standard pick and place type operations, some palletizing operations, loading and unloading a machine. It's not typically a big deal. It can cause a problem when you're doing the more complex motion profiles like deburring parts or some stuff like that. But then it really comes down to the particular cobot in question. Some of the major brands of industrial robots like ABB or Fanuc or Motoman, they're very well established robot manufacturers, and when they build their cobot, the cobot typically has the same instruction set ability as their traditional industrial robots. So the cobot in this case could then function either way, either simplified programming, usually through a graphical interface, or through the more traditional coding style that industrial robots are accustomed to. So it's just a key point to be aware of. especially when it comes to the lower cost cobots that do not have industrial counterparts within the same brand. It's just something to be aware of, that it could be an issue. Next slide. So here I have a couple examples of, this is a typical cobot program. So on the top left is a Mitsubishi cobot. This is the cobot that we have in our facility. And it is a drag and drop programming language. So each move or task, if you will, each program step is represented by a graphical icon, whether that's to turn a switch on and off, to do a move, to open and close the gripper, with some rudimentary branching and looping instructions. Because it's all graphical, it comes with a limited amount of mathematical manipulation for data manipulation. It's very easy for someone to program without any experience because it abstracts away some of the concepts that are needed for more complex use, like work frames and stuff like that. But it's a very visually easy to understand, easy for somebody to program without needing to know computer code. In the middle is the universal programming language. Again, it's basically a flowchart of steps, and it follows a very graphical visual type style that makes it easier for people to use without needing to know specific commands. And then finally up in the right, the top right, is ABB's version of their graphical interface that they use for programming their cobots. Again, it's very much a flowchart based, fairly visual, doesn't have a lot of complex code structures. The advantage to both Mitsubishi and ABB, and to some extent UR, is that behind this screen that you see with the graphical programming interface is a fully complex standard program written in essentially computer code. Go to the next slide. And here's the two examples of Mitsubishi on the left and ABB on the right of essentially the exact same code. You know, the graphical codes will essentially generate this type of code in the background. And if you're very familiar with robot programming and coding of industrial robots, you can skip the graphical front end and go directly to this back end code and write and manipulate the code and information just like you would a traditional industrial robot. So that's why I said that the last point on the disadvantages to cobots, that's a it very much depends on the brand and type of cobot that you get as to how much it will support the more feature-rich back-end code that the standard industrial robots work with. I don't know if there's anything you want to add.
That's great.
Yes. So kind of getting into our example, if you want to go on to the next slide. In this case, our example is using a robot to selectively deburr a part and taking feedback from a scanner as to whether or not it's finished with the task of deburring. And then so it runs the deburring path, scans the part to check it for size. If the part is correct, it stops. If it's not correct, it steps in a little bit closer to the tool and runs the path again. This is a fairly complex task to program, and this is what industrial robots are particularly good at. And if doing using a cobot simplified programming language, this is typically not possible. So that doesn't mean a cobot can't do it. It's just you need to break out other tools to be able to program a cobot to do the same work. So in this case, I'm using a workflow where I program the initial path that the robot takes inside of Mastercam, and basically telling Mastercam that I'm milling with a odd-shaped tool that represents the belt sander as opposed to a round cutting tool. And then that then generates the 5-axis path that I need that I'm going to use to drive the robot. Go on to the next slide. And then in here, this program is called RoboDK. This takes that toolpath from Mastercam, which is a 5-axis toolpath, and adds the additional axes that it needs to turn it into a full 6-axis robot path. And it also allows me to plot out where in space the robot is working. In this case, the robot's holding the workpiece and bringing it to a stationary tool. So that changes the dynamic of how the path is programmed and run to some extent. And this tool essentially lets me program that way without, trying to teach all the points manually and drive the robot around with a teach pennant, or by grabbing it and dragging it as you do with a cobot to try to generate this complex task. And it really frees up a lot of time and energy when it comes to programming, to be able to use standard workflows that you're probably using already in industrial environments. Mastercam and any CAM program, really, for that matter, using their pathing algorithms to program robots very easily and quickly. Or if you don't need those, you can generate any program by selecting edges and paths in this RoboDK or similar environment to generate toolpaths in the virtual offline world, and then transfer them to your robot when the path is complete and you're happy with it. Go on to the next one.
So Sam, thanks. I appreciate your input on the collaborative robots and giving us a background, particularly in some of the more advanced programming techniques that you use here, and what you would find out there to program more advanced paths. Next, I'm going to be talking a little bit about 3D scanning, because we did use a 3D scanner as part of this automation setup. I thought that I'd give you a quick overview of 3D scanning, just in case it's not common knowledge. If you go to the next slide, the sensor that we're using here is a Bearscan Pico. The only reason I bring this up is it's a small sensor. It's about 10¼ inches wide and about 5.6 inches, in depth. And so it's fairly small. It's about the size of a brick, a red brick. And the weight is quite light as well. It's about 4 pounds. So one of the points that Sam made was, you have to count when you're looking at cobots, the payload capacity. And in our case, what we're going to be showing for the case study is that we actually used the robot to pick up the part that we're repairing. In other cases where a part might be too heavy for the robot, you could pick up the individual tools that are used to repair that part. In this case, picking up, as an example, this particular sensor and then moving it around the part to be able to scan it and determine where you need to make some corrective actions. And so in this case, if we were to use a collaborative robot that had a 5 kilogram payload, this particular sensor is 4 pounds, so it's about close to 2.5 kilograms. So you can start to see how quickly you can take up some of that the weight capacity that the robot can handle. Next slide. So generally, what you'll see, we took a video of the repair process for the case study, and in that video you'll see the Bearscan Pico take scans of a part. And I just wanted to describe what's happening in the background, because you're not going to actually see it. The scanner just uses the scan data, it does what's called the deviation analysis, and then sends a signal out. So I just wanted you to know that, as an example, that turbine blade that you see on the left, not just the blade that you see on the left there, is the physical part, and it has a welded bead on the tip, which is going to go into repair process, where that bead is going to be ground down to the original nominal shape that airfoil should be in, because in this case the tip was worn. And what happens is when a 3D scanner is placed, or the part is placed within the field of view of the scanner projects a a number of different fringe images, or these black and white line patterns that you see on the surface of the part in the picture in the middle there. And a camera takes an image of that line pattern as it's being deformed on the surface. So you see originally that the projected pattern is straight lines, but what's coming back into the system are deformed lines. And because the system is calibrated, in other words, in the sensor, it knows the distance between the camera and the projector. It knows the angle between them. It knows the distortion characteristics of the lens for both camera projector. The only real unknown is the shape of the part, and this is what the scanner solves for, knowing all those all the other information that's contained in the calibration. And so all the way on the right, you see the 3D reconstructed image of that surface. So these are line of sight systems. In other words, it's what you see there is a single scan. If you were to rotate that scan around on the right, there'd be nothing on the backside. So you'd have to actually physically rotate the part, take another scan, and then it would add that data on. So you do have to manipulate the part in front of the scanner or manipulate the scanner in front of the part in order to capture the geometries that you need. So just in a very quick slide, I just wanted to give you that background of what the 3D scanner will do. During the actual video of the case study, there's a little sidebar when it does the deviation analysis, and I'll walk through what is a deviation analysis kind of manually, so you can see the steps, but that's what the scanner will be doing in an automated fashion. So next, I'll invite SphereGen to come on and talk about the HoloLens, which we used for the visualization of the deviation that we saw through the scanner.
Hello, thank you. So just a background on SphereGen and kind of why we were involved with this project. We are a Microsoft mixed reality partner, and we're located in New Haven. We're about 13 years old now. And really what we specialize in is innovation, especially things that either haven't been done or might be challenging to do. And that's why we were really excited to get on board with this project. You can go to the next slide. Our background is in application development. We also do some robotic process automation. This project was focused on the HoloLens. We are a mixed reality partner for that with Microsoft, which means that we really focus on this device. So a little about what the HoloLens is that will kind of clarify why this headset was the right fit for this project. The HoloLens runs Windows 10. It's a fully wearable computer, and it's able to do a couple functions that made it a really good fit. The first one is that it's able to really recognize gestures and spaces. So we were able to take advantage of that technology to do overlays and overlay the scans onto physical objects, and also to have hand-based controls to make it really easy for people to use as well. All right, so what can the HoloLens see? So this long and short of it is the HoloLens can see everything the user can see. It also responds to your voice and your focus, meaning that if you focus on an object, you could program in a response to that. And it responds to hand gestures, so it actually tracks both of your hands and all 10 fingers. It also measures rooms and objects, and that's what allows us to do those overlays pretty accurately. And it recognizes objects as well. You know, its ability to project interactive content is why we chose it for this project. And I'm going to turn it over to Andrew, who was our lead developer on this project.
Thank you, Amy. Hi, folks. My name is Andrew Guagliardo. I'm a mixed reality developer with SphereGen Technologies. And so we collaborated with CCAT and NERDIC to put together kind of a proof of concept around using cobots and being able to visualize deviation maps as part of a repair process. And so as part of putting this together, we collaborated with CCAT to basically get deviation maps and scans of a part that were basically being continuously scanned as it was going through a repair process. We took those models and those deviation maps and created an application inside the Microsoft HoloLens that allows users to view those deviation maps, overlay those deviation maps onto a physical object, and also be able to have some other additional tools to help them understand what they're seeing while they're looking at that deviation map. Can you go to the next slide, please? So the deviation map you've heard a lot about, and Nasir is probably going to talk about this in a little more detail, but this was a very important aspect of this because it's how a user is going to quickly be able to see where parts of the equipment they're working on need repair. And so in order to highlight this, we added the heat map into the application. So that way it can easily be looked at and compared to the model that is being visualized. On the right-hand side here, this is an example of one of the heat maps. And you can see that we've got a range here going from blue at the bottom to dark red at the top with green right in the middle. So that bright green is essentially a point at which the model is basically in perfect uniformation with what's expected. And as we move up into red, that means that there has been a buildup of some kind on the actual piece of equipment. And as we go down into blue, that denotes things like cracks or scrapes or pieces where material has been removed. And so this is important because it helps with the visualization process. So next, we're going to see a video of a view from inside the HoloLens. And this is actually shot from inside the HoloLens. And as you can see, the user can clearly see the environment around them. And we're going to see them kind of lower the opacity. Sorry about that, folks. I got muted when the video started playing. At the beginning there, we saw the user decrease the opacity so that they could check that the model was properly overlaid. And here you can see that they're picking different points. And as they click on different parts of the model, they're getting a sampling of that point, which then they can compare to the deviation map to see what repairs need to be done. So you can see as they go through and they update the scan, that top right corner had a very high point that is slowly being sanded down. And you can see that the model is slowly becoming more green as updated scans are coming in. And this is useful as a visualization process because it's basically allowing you to see things that might not be super clear when you're just looking at it, just using your eyes. You're getting an actual deviation map and measurements compared to what's expected versus what the actual piece is showing as far as the deformations. So this was an example of somebody, viewing an anchored model on site and working with a physical piece of equipment. But by using the HoloLens, one of the great things we get is also the ability to view this visualization without being on site. So the next video we're going to see is going to be an example of that. It's going to look very similar, but the key here is they don't have a piece of physical equipment in front of them. What this means is somebody off-site can be following along, potentially, as the repairs are taking place. So you'll see we've got the same functionality, but we're no longer on a shop floor. We're sitting in a conference room, and we're able to see that this top right corner has a deviation that needs to be repaired. They're comparing to the deviation map to understand what that deviation is, and then they're checking these updated scans so that they can see how the repair work is progressing. They're able to take samples at different points and compare that to the deviation map. And they're able to pull updated scans as they come in and watch as the work progresses. Now, because this is a fully realized 3D model, you don't just have to use the actual life size. You can manipulate this, rotate it, turn it around, change its size. So if you wanted to get a closer view, something that might be difficult on the physical object itself, you could do that by using this deviation map and manipulating the content inside the HoloLens. So that was what we built for the proof of concept, but this is kind of a first step, and a future workflow would essentially involve being able to connect to cloud, like an Azure, government community cloud or the GCC High, and be able to take in scans from a cobot, push those scans to the HoloLens where they could be easily viewed and visualized, and then make your physical changes either by welding, grinding, or doing whatever repair work you need to do, and then repeating this process. So you're getting that quick feedback from the cobot scanning to then make decisions about how to progress with your repairs. Next slide, please. So as I mentioned, a database basically could be synced into the cloud to store these scans as they come in, and the HoloLens could then be used to pull those scans down and visualize them. In addition to that, you'd be able to potentially even trigger the scanning process from the HoloLens itself. So you could be wearing the headset, do some of your repairs, step back, tell the cobot to take a new scan, check your new deviation map, and then continue to progress. If you're using larger objects, so for this proof of concept, we use something kind of small that wingtip is not that large. It's maybe about 10 centimeters on a side and 15 on another. But if you're using larger pieces of equipment, maybe about a couple feet on a side, you could potentially use Azure's object recognition technology to be able to automatically register your holograms onto the object itself. In the video, you might have seen that we had a little QR code for the first one, and that was used to anchor the holographic content. And as I mentioned, you can also basically use this process to allow remote workers or supervisors to follow along with the repair process, or to potentially do kind of a quick estimate of whether a part can even be repaired. So as an example, a part could come in for intake, it could be scanned with a 3D process, that deviation map could then be sent to a database, and somebody off-site could review the deviation map and determine whether or not the object can be repaired. And that's basically it for what we kind of built as part of a proof of concepts of being able to use the HoloLens to visualize data that has been scanned in by a cobot.
Thank you so much, Amy and Andrew. Really appreciate you walking us through how the HoloLens can be integrated in this particular case. So next, I'm going to talk about a little bit, give you an overview of the actual case study. So the next slide is going to show a kind of a process flow diagram. This is a precursor to the video that we're going to play next, which is a recording of the process of the the turbine repair. But I just wanted to get you kind of present this overview of how all the different technologies are working. Again, as I said, you never just use a cobot. I mean, it's always in an integrated environment where you have sensors, you have other processes, and then you have this, the communication channel between all of these different things, where when one thing happens, it needs to communicate to another process so that things can continue forward. So here I'm going to take a couple minutes and just describe kind of how this all is working. And on the left there, you see a box indicating the actual grinder. To the right, you see the robot. To the right of that, you see the 3D scanner, and then the HoloLens all the way to the right. So these are the key technologies that we're using in this kind of integrated work cell. And what we're doing is we have a turbine blade. It has wear on it. In other words, it's been used. It's been determined that it can no longer be used. And instead of producing or purchasing a new part, it could be faster to repair the part and put it back into use. Now, you're going to hear from, this is the main concept behind the project that a company here in Connecticut had reached out to us about. You'll hear from Peter Mirabello of Metal Finishing Technologies after the actual video plays on the case study. and how this concept applies to his particular process. But here, what we wanted to do was show overall how a robot can be set up in such a way to streamline the repair process. So normally, if you think of taking a used part out of an assembly, for example, a turbine blade out of an engine, and you do an inspection on it, and at that point you determine this is out of spec, it's no longer usable. What you would do if you were to go down the route of component repair would be to map out where exactly the wear is on the part using some inspection technology. Could be hand measuring, could be CMMs, could be laser scanners or structural light scanners, as I showed here. And you'd have to somehow determine where exactly is the wear on the part, and where you have to add material and how much material to add. This can be somewhat of a manual process. Then once you do determine that, you'd have to come up with a process to actually do the repair, and that could be that you take it over to a welding process, you apply, you add metal where it's needed, and you make sure you have enough positive material there, such that when you bring that part over to a grinding or machining process, that you're able to machine that amount of material just added back down to nominal. So this process, it involves the scanning process as a separate process. It involves the identification of the wear as a separate process. Then it involves the remachining of that part back down to nominal as a separate process. With the use of a cobot and with these external devices and sensors, we can streamline that. And the way in which we're doing it is that we're using the ability of the robot to communicate with all these different devices, such that we don't necessarily have to control or decouple these processes from each other. So here, if we focus for a moment on the robot, we have three signals. We have a trigger out, which is a trigger to scan the part. In this case, because we're using the robot to actually hold on to the turbine blade, we want the robot to tell the scanner when it requires a scan. And so this is the trigger out. So in the instance where the robot would position the blade in front of the sensor, it could send this trigger signal, and the scanner would just fire off a scan, and then internally it would grab the 3D geometry, it would reconstruct the 3D geometry, it would align it to the CAD model, and then it would perform a deviation analysis and come up with that heat map that you saw in the previous slides. That heat map shows us where the part is outside of tolerance. So anything that's outside of the green color that you saw previously would be indicating surfaces that are outside of the allowable tolerance. So red would indicate positive material, blue would indicate negative, and in either case, something has to be done there. And so you see from the 3D scanner side, when it does the deviation analysis, it goes down into a decision block where you determine, is that part within tolerance? And if it's not, then what you do is the scanner would send a signal back to the robot and say, continue grinding. And it would also send, ideally, a trigger to the grinder to say, start the grinding wheel. And the robot would then just, from the 3D scanner, move over to the grinding wheel and start its process that Sam had showed you, that program that is made to follow the surface profile of that blade. So that grinding process would go through, and then the robot would move the part back over to the scanner, and it would trigger another scan. And this process would continue until the time when that surface is back into nominal. Now, the important part here, and where the HoloLens comes in, is the visualization of that data. Now, say for instance, you were collaborating with engineers off-site. So you had this part that was in a repair facility, and it was going through the process of repair, but you needed to collaborate with engineers to determine when that part is back within tolerance. What is the acceptable range within which this used part can be used again? And so there, that communication and that collaboration becomes very simple when you see a 3D image right in front of you. It's communication is streamlined. There's no misinterpretation of the data. It's very easy for someone offsite just to see the current condition of the part and when to call it good to go. Alternatively, or at the same time, on site, the repair personnel could visualize that where that part is by seeing that deviation map right on the surface of the part. So you're not just looking at it, on the physical part and trying to see whether or not the surface is smooth, or going, and trying to determine, where, if the process is such that the wear pattern, is difficult to identify. The mapping of the deviation analysis really clarifies, where things are currently. And so what you're going to see next in the video that we're going to play is the actual this process running on the part. And we try to make it such that there's minimal editing so that you can actually see all the iterations that it goes through. As you saw, it took a couple of iterations to get to the nominal state. And during the process, you'll see my colleague Kristi kind of come up to the part with the HoloLens on, and then you'll see the image that she sees through the HoloLens on the current condition of that part. So here in the center there, you see the robot. Off to the right, you see the actual the Bearscan Pico 3D scanner, and over to the left, you see the flexible grinding belt that we're using in this case to machine down that or grind that surface down. This process actually starts off with having already identified that this particular part is worn and can no longer be used. And we already took an initial scan of the part to determine where that wear was and how much material was needed to be added back on. And so Sam went through a welding process to add material onto the trailing edge of this particular blade. And so this is where this video starts off. And we're going through the first iteration of grinding down that positive material that was added to get it to the nominal state. And so what you see now is the execution of the program that Sam had shown in the previous slides. That the actual path was developed in Mastercam and then translated over to be used on a 6-axis robot in RoboDK. What's going to happen next? I think this is the last pass around the surface of the blade. That the robot is going to move the blade over to the scanner, and you'll see the scanning happening. During the scanning process, there is going to be a quick sidebar, and I'll describe exactly what the deviation analysis is if it's difficult to visualize through some of the slides that we've already shown. I'll kind of describe that process as well.
And just a note here too, the speed that this robot is moving in real time is very close to about how fast a cobot moves at its 200 millimeters per second speed. It is a little bit slower, but not by much. Just as a point of reference, a standard industrial robot will move much faster than that, going from point to point. As far as the actual machining goes, that's how fast I would normally run it.
So at this point, the robot is just turning the blade around so that we can get the scan from the other side. As I mentioned, the 3D scanning technology is a line of sight, so you do need to present the surfaces, and they do need to be highlighted, or the light does have to reflect off the surface to get that. So here's the sidebar that I mentioned before, prior to Kristi looking at the actual results. And this is just to give you an idea of what is the deviation analysis. So in this case, I'm just manually showing you in the software what's happening in the background. This is a model of the CAD file that's within the scanner software. And once the scan is taken, you see that the scan comes in with its own coordinate system. It's not aligned at all to the CAD coordinate system. You see the positive material that's there. You can visually see it there on the actual file. And what we're going to do is we want to show this in a heat map, in a color plot. So the first thing that happens is that the scan data gets aligned to the CAD model, and then we run a 3D deviation analysis. And that 3D deviation, all it does is looking how far off the scan surface is from the CAD. And it colorizes the distance that it's off using this color map that you see on the right side of the interface there. So that's in short, that's what the scanner system is doing in the background automatically, and then presenting that data to the HoloLens.
Great, so I think I'll jump in now and share that what I'm doing now is using the app that SphereGen and Andrew described and created to visualize the scan data that Nasir just showed on top of the model. You might have noticed earlier that there was a QR code on the table, and that was used to align the scan data with the original model that you see up there. And we can see that in the top right-hand corner, we had that darker red spot, which indicated that there was extra material there. So I was able to use the hand motions to look at that specific point and see exactly how much additional material is at that area. And then the robot is going to continue for the next grinding cycle.
So as Kristi mentioned, there is still positive material, but what we're showing here is the view that a repair personnel can see right on the physical object, so that you can clearly see the current condition of that blade. But at the same time, that data could be viewed offsite. So if you're in collaboration with other engineers or other decision makers on what to do next, the HoloLens just makes it very, very easy and efficient in that you're seeing a full 3D model of the part. You can view and manipulate it any which way you want. You can zoom in on specific areas. In here, we're just having the top right corner of the suction side of this blade on the trailing edge, where we had some positive material. But if you imagine, if we have a more complex wear pattern and we have a more involved repair process, this collaboration and the way in which the HoloLens allows this to happen is invaluable. To be able to see and communicate in real time between the repair facility and the decision makers offsite is this is streamlining the process. You don't have to have, you can kind of the process doesn't have to stop. It's just a matter of a few minutes of a decision, and you can continue forward.
One of the pieces I wanted to add to that as well is using the change in opacity of the scan data is also very helpful, because when you have the actual model and you see, the darker red or darker orange spot, you can see that visually, and then you can make that more transparent so that you can actually look at the physical part itself and see really where that extra material is. So being able to see both of those, as Nasir just said, in real time very quickly was a great experience.
So again, here we still have positive material, and so we're gonna the robot's gonna go back and continue on with the grinding process. And this video will it will speed up a little bit, so you'll start to see the grinding process go faster. It's just the actual speed was the same as you saw at the beginning. We're just speeding up the video here for the sake of getting through. But did want to show you the iterative process, and so that you get a feel of kind of what's going on, and the amount of, it's kind of the near real time way in which this process, this repair process was carried out.
And just to, if I can jump in here too, when the program runs, each time it iterates, it sends and it gets the result that the part is not good. It steps the tool in closer to the sander by a predetermined amount that I set ahead of time. For this iteration, it's definitely within the realms of possibility that it could be taking information directly from the scanner as to how much material is left, and use that as a control to determine how much to step in at each iteration to give a finer control over the process. We just didn't implement that in this case, mostly due to time constraints.
So again, I believe this is the third iteration, if I didn't lose count. We've gone through the third time of grinding the surface. Again, as Sam said, with putting the actual part closer to the grinding wheel, or to the grinding belt, and removing a little bit more of that positive material. And now the scan has been taken, and Kristi's gone back up to the part and visualizing that data, and you can see that more of the part is green now. We have less of the red up at the top right corner, but since we still do have a little bit of positive deviation, the system is going to continue with the grinding process, again stepping that part in a little bit closer to the grinding belt. Now I think I start to chop out some of the portions of the videos so that it can go faster. But this will be the fourth iteration, and you'll see a fifth one happen in just a moment here. I will say too, and Sam, you might have some better comment about this. You have keep in mind the robot is a 6 axes. You have 6 axes of manipulation of the tool or the part, and it's very impressive to see how close the robot is able to follow the surface of this somewhat complex shape. So this airfoil shape has a specific pressure and suction side geometry, the airfoil geometry itself. The leading and trailing edges are critical, and they have a specific radius. And the robot is able, and the blade itself starts out with a thicker airfoil shape and thins down as you go to the tip. So it's a complex surface, and the use of the robot in this case for this particular repair is also a great application of using a multi-axis control and kind of a complex grinding process, as Sam showed before in the software solutions that he uses.
Yeah, the robots are particularly good at manipulating material, with this complex toolpath. It's one of the primary benefits of using a robot over a, say a fixed CNC machine, is given the additional degrees of freedom, you can reach around and under parts, without having to take stuff off or do another setup. It makes it quite a bit easier to run these exact complex paths. One thing to note, though, that robots are typically a little bit less accurate than a CNC machine, so you typically would use compliance or some other means to make sure, to take up any little deviation that the robot may have in its path. For a sanding application or grinding application, it works quite well where you're blending and removing tiny amounts of material at a time. So the sander actually has a little bit of give in it to take up, the irregularities of the surface. But it does really help smooth things out, keep it nice.
Yeah. So that last deviation map, if you caught it, was all green. If you go to the next slide, I actually give a summary of that. So what you saw was from the left, you saw iteration 1 where where Sam had added on extra material, where originally we had determined that was blue. That whole red and kind of yellowish region there, when it came off, would have been blue in the initial scan. But since we added that material there, it's red, which is what we want. But now we want to get it back to nominal, so that grinding process is used to remove that positive material, but just get it enough removed to get it down. So iteration 2, you see that region starts to shrink. You get more of the green or intolerance surface. Iteration 3, again, you're seeing more of the green and less of the red. Iteration 4, and then until iteration 5, where you have a completely in-spec surface. So this was, in short, the process of component repair, in this case doing on a turbine blade, on a small wear area. But if you can imagine complex wear patterns, where it would be a very long process to do manually, the robot system, along with all of its integrated sensors and other tools like the grinder that you saw, can really streamline the process. I mean, it's immediate. You have immediate feedback from the scanner where that surface is. You can get real quick visualization of that data if in fact, particularly for repairs, if you have to communicate that offsite to decision makers, and then we can immediately let the system continue or stop as we determine through that visualization or the deviation map telling us where that part is. Next slide, please. So with that, this was a case study on a example part. I'd like to bring on Peter Mirabello, who is the chairman and CEO of Metal Finishing Technologies, who can describe the true benefit of this in a real-world application.
Good afternoon. Thank you, Nasir, to everyone on the panel here today. Yeah, these are powerful things. These are tools that are going to make everyone around here more competitive. Our job is to take it out of the laboratory and put it into a real-world environment. And I think that's the real takeaway message right now. If you follow this process around, you take some digital scans, you get a lot more information a lot quicker. And all of a sudden, you've got quality data. You can start to now mine for that data. You can understand part trends and things like that. You get an added benefit that now in this world where everything is virtual, you don't have to match the part with the engineer. You can get them to look at it virtually, almost in real time. So the first benefit is time itself. 2, with better data, you don't have to make conservative rule of thumbs decisions about the life of a part. So you get part extension life, which is critical to lowering the overall operating costs of the part. And then lastly, by being able to do the repair, there's an underlying sustainability benefit to this, which means you got to mine for less raw materials because you can reuse these parts. So these are powerful things. And again, I'm excited to be working with Nasir and team and Ron and this whole organization with Sam and Kristi, talented folks, to really bring it into a real world application to help some of our local OEMs. So really that's what I wanted to share, that this is more than just an academic discussion. There is real utility to take the inspection process and the repair process to the next level. And I'm delighted to be working with these folks. So I'm willing to answer any questions, but I think most of this was covered today. I'm just here to tell you, I look at it as a complete holistic system from inspection to analysis to repair to return to service. And this is really powerful tools that are going to become more and more commonplace. So with that, I'll turn it back over to you, Nasir.
Thank you, Peter, for those words, and appreciate you taking the time to come on.
Indeed.
Next slide, please. So with that, let's open it up for questions. I'll welcome Amy, Andrew, Kristi, and Sam back on, and let's see if we've got any questions here. So at the moment, I don't see any questions coming in. Remember, on the right side of the GoToWebinar panel, you can type in your questions in the questions area, or feel free to use the chat area as well, and we can get your questions answered. So one of the questions that just came in, it reads, you said this was 6-axis robot. What is more common in cobots? I'll defer this to Sam, who can talk about this more.
So cobots typically fall into 2 categories. They will either be a 6-axis, pretty much identical to the one that you saw, or increasing number of them have 7 axes. They have an additional axis on the first joint of the arm, and that's mostly for a material handling application when it comes to doing stuff like warehousing, because it allows the robot to reach underneath of itself to pull stuff from underneath, a shelf, and to put it up above itself onto a shelf. But by and large, 6-axis is the most common. And when it comes to adding additional axes, it doesn't really make a difference. Occasionally, you'll see a 4-axis collaborative robot out there in the SCARA form factor. So it's not fully articulated like an arm. But yeah, the vast majority are 6-axis systems.
Another question that came in, are the motor limiting forces, torque of the cobot programmable so that a cobot could be moved inside a cage in a traditional fashion?
Again, that depends largely on the make and model of the robot. Typically, torque cannot be changed and the payload cannot be changed. What can be changed is the speed. So the speed is something that's relatively easy to limit. And then, for example, on our Mitsubishi cobot, if we added additional external safeties to the cobot, it could operate much faster at up to 1 to 1.5 meters per second. That being said, if payload's really an issue, there are other ways to get collaborative behavior out of standard industrial robots. We briefly mentioned at the beginning, the several main classifications of collaborative robots, and most everything these days is focused on power and force monitoring. The other main type, though, is speed and distance monitoring. And what this essentially does is using a vision system to dynamically track how close the robot is to any object in its work zone, plus it monitors the trajectory and speed of all objects in the work zone and dynamically overrides the speed of the robot depending on, how close and how fast things are approaching the robot. So the robot can move at a very slow speed up to touching somebody before it stops, because it just slows down slower and slower the closer it gets to somebody. So, until it reaches a threshold where it's no longer a danger. And so that technology is it's a bit newer than the power and force monitoring. It's a little bit harder to deploy because the vision systems are a bit more complicated, but it's definitely out there. And if power and speed are an issue, you can definitely use a system like that to essentially turn an standard industrial robot into a collaborative robot much more easily.
So thanks for those questions. And again, if you do have any further, feel free to reach out to us anytime and we'll get those answered. I'd like to continue on for the sake of time, just to go on to the next slide here. I really do have to thank Amy, Andrew, Sam, and Kristi, for all your support on this technology presentation. It wouldn't have happened without you. Again, if you have any questions for any one of us, please do feel free to reach out. We'd be happy to answer your questions. We do welcome you to explore the extensive repository of recorded technology demonstrations we have accumulated during the course of the 2021 NERDIC series. These are all demonstrations of Industry 4.0 technologies, such as model-based definition, industrial IoT, automation, and additive manufacturing. And they also contain insights shared from pilot projects and the New England employers. I'd welcome you to register to access at ccat.us/NERDIC. Well, with that, we'd like to thank you for taking the time to join us today on this last presentation of the 2021 NERDIC series. Stay tuned. As you heard at the beginning, there's more to come to benefit your companies. We hope the presentation and the great questions that were asked today help to understand the benefits of using collaborative robot technology and what it brings to manufacturing. If you, as I said, if you do have any further questions, please do feel free to contact us. You see my email there below. We'll be sure to get your questions answered. Really appreciate everyone tuning in today. Hope to see you in the future, and thank you again, and have a great rest of your day.